Okay, here we go. Welcome to implementing IXMR and target to nominal charts for small production runs, a webinar sponsored by the AASQ Process Control Methods Subject Matter Interest Group, or SMIG. Next, please. So the material for this webinar was prepared by Pete Tatey, Senior Fellow in Quality Engineering at Pratt & Whitney. Today's webinar is being presented by Russ Palmater, Senior Fellow, PPAP and Process Control at Pratt & Whitney, and myself, Andrew Stout, Manager of Quality System Compliance at Pratt & Whitney Canada. I'll do the start and finish, and Russ will cover the charting tools in between. Next, please. So, welcome and overview. Next, please. Today's webinar is being recorded, as you saw. A link to the recording will be provided within a day or two. We'll be using a tool called Slido for Q&A rather than the Teams chat. Then you'll see how to get into that on the next slide. To take your questions, we'll use that Q&A tool. Feel free to submit your questions as we go, and we'll have a dedicated Q&A session towards the end of the presentation. Lines will be muted to help prevent any background noise during the webinar. Next. So, either with your phone or your computer, we'll be using this tool called Slido to allow you to participate to some extent in the presentation. And I'd like everyone to do this now if they could, either on the computer or your cell phone. If you're on your computer, in your browser, search for slido.com. And when you're in there, when you've picked it, there's a participant code to enter, which is shown on the screen, 8989514, no spaces. And then you may require a passcode, and that's shown at the bottom of the screen. And that's actually an L, lowercase l, BTDDJ, and then select Join Event. And then you'll click on the Polls button. So on the cell phone, kind of similar, a little bit different. You can use your camera on your cell phone to take to select the QR code and use it to take you to the Slido tool. Enter the passcode and select Polls. We'll be doing polls, and also there's another button for the Q&A to put your questions in. So we'll have several of these activities throughout the presentation, especially towards the end. So don't close the application once you have it going. Are you ready for the first one? Here we go. Next. So hopefully everybody is getting in there now. The information again is shown at the left-hand side of this screen. So if you're still working on getting there, the information is there. So what are the typical lot sizes seen in your company? So if you're thinking of a single number, put that in. If you prefer, you can enter a range of values. So I see 15 come up. Maybe if from low to high, if you want to put a range in, or you can probably enter more than one value. And we'll see what, 1120. 1530, some big sizes, but also some smaller ones as well. 10, that's a pretty small lot. Oh, there's a 1. That's a really small lot, huh? We've got 11 participants so far out of the 22, minus 3. Well, 20 people are currently involved in the presentation. So we're seeing good participation. Thank you. I'm glad everybody's, many people are getting in there. We got 12 results so far. So quite a range of values. There's from 1 to 100. There's quite a variety of quite a range of values. Small 10 parts a month. 10 parts a month. Yeah, that's That's very small. It's funny how that got so big compared to the other values, but maybe it's the length of it. But anyway, I think we get the idea there. Russ, you had a good feel for that?
Oh, very much. That is a nice range of samples per lot.
And there are some that are quite small,
Yeah.
especially down to 1. Okay, so we'll move on. Well, if you can continue putting your values in if you want to, but we'll move on to the next slide. Okay, so just a bit of background. The purpose of the reference manual RM 13006 is to provide practical approaches. So practical is the key word there. It's maybe often missing from textbooks. So this is to try and tap the experience of people who have lived the experience and tried to apply it in real life and learned that things don't always go the book way. So we try and be a little bit practical to process control to ensure consistent quality and raise the capability of our aero engine supply chain. And with the goal of really supporting defect prevention and reduction. So this includes supporting APQP, PPAP, and key characteristic variation management by providing detailed guidance and case studies to make it easier to understand. Next, please. So what is the process control, or PCM, subject matter interest group, or SMIG? So we are charged with promoting the effective deployment of process control methods across the AESQ supply chain. It's made up of subject matter experts from the AESQ member companies, supports the PCM requirements in the standard, which is AS 13100, develops and maintains the PCM reference manual 13006. We support the related Community of Practice, or COP, which is open to anyone from any AESQ member company, and we can answer process control related questions. There's a link at the bottom of the screen to the subject matter interest group page of the AESQ website, which you'll get a link to later on. Okay, next. Here's the current membership of the SMIG team for process control methods. And we can use a few more members from other companies. So if you have the interest and some expertise, or you know someone who would be a good candidate from your company, consider nominating them. Next, please. So where to get help? The AESQ website has a documents page, and under that is supplementary materials. And you can go there to find and download a copy of the RM 13006, as well as some supporting templates. And we'll talk about those a little bit later on. So the subject matter interest group meets monthly and supports the development of 13006, as well as templates and tools. And we're also, like, if you haven't already done so, to join the LinkedIn page for our Community of Practice for process control methods. And we're currently at 427 members at last count. And there's a link at the bottom of the page to get to that site. And we appreciate you joining, and hopefully you'll find it useful. We do some interesting things there, share updates, and do some polls, and you might find it useful. Next, please. Next page. And now I hand it over to Russ to take us through some options for handling the small lot size process control. Take it away.
Fantastic, Andrew. Thank you very much. So good day, everyone. My name is Russ Palmater. I will try to do my best impersonation of Pete Teddy, since he did a wonderful job preparing this material for you today. But we will be going through, what do we do with the data? What do we do with the information that we have, and how can we best utilize it for a process control journey? Next slide, please. So in this particular section, we're going to be focusing on the individual value IXMR charts and target to nominal charts. Now, these are not the only types of control charts that you can utilize, but they are probably the most common. Very, very popular across industries and extremely useful when we have smaller lot sizes in production. So we're going to explore, we got a couple of exercises that we'll go through for the IXMR charts, and as well as the companion chart, the target to nominal chart, which is extremely powerful when you have part families that share similar features, not necessarily the same dimensions, but similar features, similar processing, and similar tolerances. Next chart, please. If you don't have this already, I recommend this innovative control charting by Stephen Weiss and Douglas Fair. This is actually an excellent reference to have for the different types of control charts, when and where to use them. It's got, again, further information for conditioning charts for small lot sizes, making sure that if you have multiple features within a part that you're measuring, how do you define those as independent measurements versus dependent measurements, and what type of control charting fits best? Group charts, if you have, again, part families that you want to take advantage of and build up your sample size. These are all options that you have for creating a more robust sample population for statistical process control. You can acquire this reference manual from the ASQ Quality Press, and there's a link down at the bottom. So the next chart is actually going to be our next poll question here, and we'd like to get your feedback and response on this. Just to understand kind of what is your exposure, what has been your experience within your company, within your supply chain, for IXMR charts. They actually might be called by various names within your organizations. We have examples here called variable control charts, but in essence, they're all used to monitor variable outputs and process parameters. They're all used to chart that information. So we'll give you a couple of minutes here to fill in and respond to the active poll. I like the description of this type of chart before, especially live. It looks like a horse race. And call who's going to be the winner.
Neck and neck right now. I don't know. It's hard to call. Both is coming up. Oh, tied. We got 12 responses so far out of the 23 people.
And it's interesting, not just target to nominal charts. It's either IXMR charts or both, not just one by itself.
Looks like the race is kind of slowing down at this point.
Yeah. I mean, just one other thing, this is for variable key characteristics, so it doesn't necessarily have to be product outputs that we're measuring here. It can be process inputs, so there might be more usage within a particular flow line or manufacturing cell.
For those who joined late, you can join on your computer under slido.com with that number shown on the left-hand side, or you can go through your phone, scanning the QR code and entering the information that's shown in the bottom left corner. Maybe we can declare a winner here.
Yeah, I think we can. Looks like majority of folks have experience with both, so that's good, or at least exposure to both. So that's great. And those are the two types of charts that we're going to focus on here. So next chart, please. All right, so before we jump into the chart examples and the exercises, just a quick review from the last webinar that Pete was able to host. And just talking about kind of the 3 C's of statistical process control. So starting with control itself, this is a term that's synonymous with stability, and it's known as the voice of the process. You may hear the phrases in day-to-day conversations regarding processes. You may hear phrases like, this process is in control, or this process is stable. Those might be used interchangeably. Again, it simply means that we can predict the outcome of a process within a degree of certainty. So we know that when we put a piece of raw material into the line, we know what's going to come out the back end, again, within a degree of certainty. Capability, we hear a lot with process capability. That focuses on meeting the customer tolerances. What is the engineering tolerance that I must achieve? And this is known as the voice of the customer. So when you compare the voice of the process to the voice of the customer, this tells us, how stable the process is and how capable the process is. And that gets us to looking at, centering. Centering looks at where are we relative to either the nominal dimension or a target dimension. Purposefully to one side of the tolerance or another, to protect against scrap conditions, where are we targeting within the boundaries of the customer expectations, the customer tolerances? Next chart, please. So control charts themselves are just a visual representation of the process performance over time. They're a bit different than a time series plot, which is simply the data plotted in its order, because it introduces elements such as control limits, an upper control limit and a lower control limit. So the control limits are going to be calculated based on the distribution of the data. If I were to take the chart on the right-hand side here and plot it by frequency into bins, that would produce a histogram of the data. So the bell curve that we traditionally see is simply that data turned into a vertical binning chart. Again, the control limits are going to be very heavily dependent on the distribution of your data. So you want to make sure that the data is the expectation from these charts is that the data is going to be normal, or your process physics are going to be generating a normal type distribution over time. And that's how it calculates the upper and lower control limits. So it's important to understand that distribution before you start interpreting the charts themselves. There are also control charts for attribute data. There's a couple charts coming up where we'll kind of show that distinction, but we're going to save the attribute control charting for another topic, for another day. Next chart, please. All right, so some of the other, just again, reviewing from the last webinar, some of the other considerations, not just the distribution of the data, but some of the other considerations we have are the types of variation that your process is going to be prone to. There's 2 types that we focus on, which is common cause and special cause, or assignable cause, something where we know, there's an identifiable reason, there's a known reason for why we have a departure from the, I'll say, the family of data, the data points. So common cause variation is the natural variation in the process. It's the natural part-to-part fluctuation, based on setup, conditions of the process itself, and as things change over time. It's always present. It's always going to be there. What we want to understand is, that voice of the process is trying to tell us something about the process itself. It's trying to tell us that distribution of data and what can be expected. The question we ask is this distribution, is this variation the best that we can do? Is it what is expected from our process? It should be stable and predictable over time, and it really can only be reduced through process improvement. Now, both common and special cause variation will affect our calculated control limits. Again, because the calculations themselves are going to be based off of the individual data points and how they are aggregated together. Special cause happens randomly, but it's usually, from a known or knowable reason. If we can explain it and categorize it, then we can reduce the occurrence or magnitude of the impact that it has on the process. So both types, again, both types of variation are going to be affecting our calculated control limits. Next chart, please. So I talked a little bit about, the 3 C's and the control versus the capability. A process is said to be in control or stable if it's in statistical control, and we use the calculated limits as a way to test whether or not that data is within a predictable pattern. The comparison, again, between the voice of the process and the voice of the customer is what we use to categorize a process and its performance over time. Individual points near or just over the control limit, might be considered practically stable. It really depends on the magnitude of the measurement versus the calculated limits. So again, if you have special cause points or you have common cause variation that is approaching the calculated upper and lower control limits, for all intents and purposes, it might be practically stable, but we really want to drive towards a state of statistical stability. Next chart, please. So here are the different types of control charts. I kind of, teased this earlier with there are variable and there are control type or attribute type control charts. So we're going to be focusing on the usage of individual value charts, since, small lots, usually less than 50, is common throughout our industry. And you saw that in some of the answers and such. 15 to 25 is usually what I've heard, or I think at the 30 to 50, anything less than 50 is very, very useful for these types of charts, both types actually. Next chart, please. So let's start with the IXMR chart, and then we'll talk about the target to nominal charts here in a little bit. So what you're seeing on this chart, the graph that's being shown is an I chart. It's an individual value chart. It is typically coupled with a moving range chart that is going to be plotting the change between adjacent data points. So how they are actually moving, the difference between those points is what comprises a moving range. And we'll go through an example of this too. The control limits here are, again, calculated assuming that the data is distributed normally. And it's always good, kind of as a foundational principle or fundamental principle, it's always good to check the normality of your data before you apply a control chart, or really before you try to interpret a control chart. What are my process physics expected to do? Am I going to be expecting data points to fall within a random pattern around my target or around my mean? Or am I expecting there to be some trending or patterning over time? So the other component of this, the individual chart, the moving range chart, the other component are going to be the Western Electric rules. And we'll cover those 8 different rules here in a couple of charts. But All three of those combined together is how we understand and interpret a control chart. Next slide, please. All right, so how and when and where do I implement IXMR charts? So IXMR charts, again, are good, really good for small lot sizes. This is where we're going to be treating each part, each measurement as an independent value. You know, they're a step beyond just a simple run chart because of the control limits that can be calculated. So now we have more information based on the distribution of our data, based on how much information we have and can put into the system. It's used where, you know, lot sizes are relatively small, again, less than 50. Data is available only on a limited basis, meaning we might just be producing one lot per month, or the cadence might be very extended time periods between production. It can also be used where operation runtimes are very high. So again, that can lead to a longer time fence between when I'm getting my actual data measurements. Generally, 100% of all pieces, all data is plotted on the chart. Again, they're treated as individual measurements, and the subgroup size is equal to 1. We'll cover what that means here in a minute, or the implication that that has. But essentially, again, each data point is independent. Next slide, please. So, you know, sometimes subgroups are impractical or don't actually represent the nature of the feature that I'm measuring and trying to plot. The individual X chart always uses a subgroup size of 1. You know, again, that indicates that all the measurements are treated independently and there will be no averaging between the measurements. Whether you are using an IXMR chart or an X bar R chart, so that the X bar R chart is another one where that actually does introduce subgroup sizes larger than 1, and that one will be useful for where you take multiple measurements of the same feature, say like a diameter or a thickness. If you take multiple measurements, the feature is repeated multiple times around a surface of revolution. The X bar R chart is useful for subgrouping your data to get an average, essentially, of the measurement. But the IXMR charts, they use a subgroup size of 1. And then the moving range chart, as you can see the calculations here, each subgroup is treated as one observation. You know, there can be no subgroup range. So we use the moving range to indicate how are things changing from part to part or from measurement to measurement. So we treat each pair of observations as kind of a pseudo subgroup of 2, and then we calculate the moving range. And it's really my current data point that I'm on minus the previous data that I entered. It's just the difference between those 2 points. And then there are, again, the Western Electric rules apply to both the individual X chart and the moving range chart. So you will be able to see how both of those respond and whether or not one or both are producing some type of condition that meets one of the Western Electric rules. So the calculations are all shown to the right. I'm not going to go through all of these in detail, but you can see the individual value itself is the individual X. The moving range is the difference between adjacent points. The upper and lower control limits that are being calculated are, they use the moving range as as the principal calculation. And then there's 2 variables in there, D sub 2, and I believe it's D sub 4. These are actually, one of the reasons it's good to have the reference manual is because these are statistical constants that are used to help determine the plus or minus 3 sigma control limits, or close to plus or minus 3 sigma. And that's, again, going to be based on your distribution of data and your moving range. So again, the great part about control charts, whether it's the IXMR chart or the XBAR-R chart, is you'll see consistency between what's being displayed on the chart and how to interpret it. So the interpretation is going to be the same. Next chart, please. So now we have an exercise, and this is going to be fun because I know the answers are just interspersed here if we click too far. So we have a specific part number from company ABC. We're going to what's shown here is data measurements for 20 housings where there's an inside diameter being a key characteristic, and that's what was measured for the 20 pieces produced in time order. So the one right after the other, and that's what's kind of shown on the right. So if you want to advance it, I think it'll bring up what I just described. And so you can see the calculations or the data that's being in the chart, in the sheet itself. And you can see that we've got all the measurements for parts 1 through 20. For the moving range, we only have the moving range calculated up to part 15. So I think if you advance it once, it'll take us to the first question. Yeah. So for the audience, this is your first chance to participate here in an exercise. What would be the moving range values for let's just start with part 16. And I think, Andrew, we said we can use the chat for this, or
Perhaps the Teams chat is better for that.
The Teams chat would probably be better for this. So let's just start with part 16. We'll do this for each individual 16, 17, 18, 19, and 20. So if some of you want to get ahead, we'll start with 16. Who has a guess? Or who has a calculation?
A little hard to see the numbers on the page, depending on the screen size, magnification.
Should I read them out then?
Oh, we have an answer come up for the first one.
I see a couple.
One answer.
We'll go through it real quick. Also, let me just pull up the chat. Oh, perfect. So we got three responses, and yes, indeed, that is correct. So the good job, Stefan. I see you got ahead and you did 16 through 20. So if anybody is concerned about, where did those numbers come from? Again, on the previous slide, the calculation for the moving range is my current part, my X, my individual value for my current part. So we're on 16. My individual value is 2.1040. My previous value on part 15 was 2.1041. So it's going to be the absolute value of that difference. You're not going to see negative fluctuations or negative values. It's always going to be the absolute value of that difference. So excellent, good job. So Stefan went ahead and got ahead for us. So perfect. That's great. If you advance the slide one more, it'll bring up 16, 17, and 18. We can check his answers. Very good. If you do it again, it'll bring up 19, and 20. All right. Again, that's what we would fill in that box, or in the Excel template that is commonly used. That will be filled in for you as you enter the individual values. But again, where does it come from and how does it populate the slide below? Advance it one and we'll get to the next question. So, so why is there no moving range for part number 1? If you notice, our moving range starts with part number 2. You can use the chat to respond as well. The previous day, there is no part 0. Need two entries for the difference. Perfect, because there is no number 0. Exactly. So go ahead and advance it. It'll show that answer. So nothing made to compare to. So the importance of the moving range is, again, it's going to give you any type of signal for large departures between individual values. So although your individual values might be within statistical control, it might be within your limits, the moving range could send a signal that, hey, something large happened here. You need to probably go and look at what happened within the process to make such a large moving range. In the data that we have here, there's not a lot. There's very tightly controlled information. It's all below 0.5 of a thousandth. So this particular process, we don't have control limits shown on here, but you could start to say that, again, the data from a moving range standpoint, the adjacent points stay very well controlled. Next chart, please. So we have another exercise, and in this exercise, we're going to be using a Minitab capability 6-pack. It's a very common tool that's used, including Minitab. And if you advance the slide, it'll bring up the chart. It'll bring up the question one more time. It should bring up the chart. There we go. So we're going to look at a completed control chart on the right. So note, we typically don't calculate the control limits until we gather between 20 to 25 data points. So we've got, 20 that are showing here, right? So that's when we're going to start to calculate the control limits. So for those of you familiar with the Minitab output here, the IXMR chart, for those of you not familiar with it as well, the left-hand side is going to start with my individual value chart. That's my IX chart. The one below it is going to be the companion chart, the moving range. And then I've got some other features here. I've got a normality test on the middle right. I've got a capability analysis and a histogram. So my data, my individual values are now put into frequency bins and turned into a bell curve. So let's go with the first question here. We'll ask, if you advance it, it should bring up the first question. And there we go. Does this process appear to be in control? Remember what we said about statistical control using my IXMR doublet of charts. I'm looking to make sure all my data points are within my upper and lower control limits. So am I in a state of statistical control? We'll look at the chat for any responses here. Very good, yep. Yeah, I like that. Yes, if we're using the first Western Electric rule, go ahead and advance it. It'll bring up the answer. Yes, so it does. Yes, we are in a state of statistical control. No points are violating the first rule. And we'll go through these rules here on the next slide. So good for those of you who are familiar with the rules and what the Minitab output is showing. Next question is going to be, does the process appear to be normally distributed? And then what tells you that on this capability analysis? Where do you find that information? Okay, we got yes, passes the Anderson-Darling test. Normal probability plot is what we're looking at. So The chart on the right-hand side in the middle is where my normal probability hypothesis test is actually conducted. So I have a p-value and I have a Anderson-Darling value, and I have my data plotted on a distribution plot.
That's a bit of text off the order, Yeah, check the order out, man.
I think we got somebody. If you could go on mute.
Is that? Yeah, I'm just trying to.
There we go. Thank you. So we could actually say a couple of things about the normal probability plot. If you notice, the data is actually in very, it's almost in buckets or categories. There's stacks of data, and that's usually a indication of a precision issue. If my measurement tool had infinite precision, then I would expect those data points to line up more agreeably along that curve. But we still have the normality test itself. So even with the precision of the tool that we have, we're still saying that, yes, my p-value is much greater than 0.05, which is that's the threshold that Minitab will generally use, even though you can change it. But that is the threshold and the amount of risk that we're taking on, assuming that this is a normal distribution. So in this case, yes, if you want to advance the slide, it'll go to the answer. So yes, it does. It follows a normal distribution. And again, the p-value is greater than 0.05. Next question. Why is the data being distributed normally? Why is that so important for our individual data? It's not a trick question. I've actually mentioned this a couple of times because it's so important. I think did we stump you with this one? Either that or I didn't say it enough times. Yeah.
I think you better give the answer to that one.
Yeah, no, there we go. There we go. CP and CPK coefficients are assuming normal distribution, correct? Data needs to be normal to get a trustworthy CP PPK. Yeah. Formula that are used for the control limits, the things we're going to be testing statistical process control against, depends on the assumption of normality. So go ahead and let's show the answer here. Very good. That was a burst of information or a burst of responses. So perfect. Yeah, the control limits are calculated. They depend on that assumption. So we always want to make sure whenever we're calculating capability, whenever we're looking at control limits, we want to make sure that the distribution matches that assumption. Or that if there are data points that are pulling my distribution away from normal, can I explain those data points? Can I say, well, this is a special cause, or perhaps I have two distributions that are in the same population. Maybe I have rework components that are, intruding on my, I'll call it pure voice of my process. Good answer. So there's one more question. Does the process appear to be capable and centered? Remember what we said about capability. Capable means it meets the engineering tolerance, the engineering expectation. And centered would be how well am I between those two? Okay, good. So yes. Yes. All positives. Good. So if you want to go to the next, just advance it. It'll bring up the answer. So yes, it does. Our CP, which is an indication of if we we talked about it earlier. If my CP is, the CP represents what my capability would be if I had all my measurements perfectly centered between my engineering tolerances. So if we compare the CP with the CPK, you can see that those numbers are very, very close to one another. So I've already got a very well-centered process. It's above 1.33 CPK, so my variation is well maintained. I have a stable and capable process. Next slide, please. So these are the Western Electric rules. I always recommend that you have a copy of these in whatever format. You have a copy of these printed out and next to any operation where you're going to be looking at and interpreting control charts. So these are the different rules that operators can look for to determine if a process should be stopped, or it should be left alone. What is my reaction plan if I start to see these types of indicators? So there's 8 that are shown here. The first one we talked about kind of already. Do we have any points, any single points that are outside of my control limits? Do I have 2 or more that are on either side of my center line? So my data is fluctuating back and forth across the center line. Do I have any type of patterning where I've got 4 or 5 points in a row, consecutive points that are to one side of the center line or other? Are all my data points just on one side of the center line? The test number 5 is usually the one that I see pretty commonly. Actually, 1, 4, and 5 are the ones that I see commonly where processes have a known type of wear. There's a tool or something that has a known wear characteristic, and it will create a trend over time. Others might be, coolant flow, or as things become less viscous over time, I'll begin to see some type of degrading pattern or trend, signaling again that something needs to intervene in the process in order to remain within statistical control. So these are extremely useful. I highly recommend you have a copy of these available. Next chart, please. I'll try to pick up the pace too, because I think I want to give us time to get through all the information. So we kind of went through this already during the exercise. But again, another great reference. This is a guidance sheet for where do I start when I have a Minitab 6-pack output. And it's always, I start with my normality. That's going to be the foundational piece for is everything else I interpret from this information. Is it going to follow that stability and capability interpretation that I need from the process control chart? So again, a good reference that you can use for your processes. Next chart is the next active pole. We'll do this real quick. So is statistical control important? I know somebody's dying to say doesn't matter if capability is good. The consistency of results over time, good.
I've heard that a few times.
Yeah, that's the common that's the culture, right? It's the culture that we're trying to shift. All right, so here, thank you for the responses. Yep, that's exactly why we want to do these. only got about 10 minutes left, and I'm going to try to get through the target to nominal. It's a fairly simple concept. We got about 5 slides or 8 slides left here. But I want to leave time for Q&A and any, I think we have a quiz too at the end. So let's go to the next slide. We'll talk about target to nominal charts. So implementing target to nominal charts, this section is really useful for where you have part families. And I think it's probably best if we just quickly jump into what it is that we're showing. So if you want to go to the next chart. So here, the target to nominal charts are exactly what they say. They show variation from a target dimension or a target value of each individual measurement. So in a way, you're essentially taking your measurement and you're normalizing it based off of a target value, which is why you can compare different parts with very similar features and very similar tolerances. So now we can plot more than just one part number on the same chart and take advantage of the control limits and the Western electric rules that would be developed. Next chart, please. And we'll actually go through an example of this, so I'm not going to belabor it, but there's essentially, you're plotting the point for the target IX chart. You're determining the individual value and you're subtracting off the target value. So again, not a complicated calculation. Similarly, the plot points for the MR chart are going to be what's the difference between the current and the previous target IX value. That's exactly the same as what we did in the IXMR chart. The center line is going to be the total individual plot point values divided by the number of that value. So it's, again, going to be telling you where you are, what is the actual center line that we're going to be referencing. Where does the target dimension actually lead us? Next chart, please. So for the constructing the target IXMR chart, the upper and lower control limits are going to be, for the X chart, they're going to be based off of, actually for all of them, they're going to be based off the moving range. What you're going to have is a constant that's in front of that moving range. So it takes the X bar, the average value, and then adds plus or minus 2.660. So that's a constant. For the moving range, it's 3.27. And the lower control limit to the target MR chart, again, same for the IXMR chart, is always going to be 0. Because we don't drop below 0. It's the absolute value of that. Next chart, please. Now, there are some limitations on how we use these charts. The moving range chart is dependent on the individual X chart. So a significant shift in an IX value is usually matched by a significant shift in the MR values. Again, that's going to be the same change, but this chart will be more sensitive to that because, again, you're plotting different parts on the same chart. Because we are using a normalized calculation, we're subtracting the target dimension from each of our measurements. The natural distribution of the entire population is going to be normal. So for control limits to be valid, that fits that category, and we can set up a histogram to look at that information and do the normality tests as well. My process capability is going to be, again, the same type of calculation, my engineering tolerance to my natural tolerance of my process. And that equals total tolerance times my moving range divided by 6 times my moving range, and then that constant, that D2 constant that we had before. That's the CP, and then the CPK is going to be the minimum of either one of those. Next chart. So we have, this is the example of the chart that we're going to be looking at here. And it's really, looking at 3 different bushings. Each one has its own different dimension, but they're all made on the same machine. This is some of the assumptions that we make. They're all made, of the same material, and they share similar tolerances. They're very, very, very close. So a total production run of 20 ABC bushings were made and plotted on a target to nominal chart. So 3 part numbers are going to be shown on the same chart. If you want to go to the next page, we have that. So here's my actual values, and I've got, my part name at the top, A, B, or C, and you can see that they're interspersed. So we might be having batches of parts being produced. The machine is being reset for each one of those. But again, it's the same machine, same material, and very similar tolerances. So my values, are my individual X's. And then my nominal is going to be, that's my target dimension. That is what I'm trying to subtract from what my actual measurement is. So my value to my nominal, my value minus my nominal is going to be that difference. And then the moving range calculation is calculated the same way. Now the value minus the nominal is going to have a plus and a minus characteristic because it's going to be, again, centered around that target dimension. And you can see that the target dimension changes based on which part I have being displayed. Okay, next chart. So this is now how I'm going to get my process capability from, for each of those parts based on the collected 20 data points for all 3 of those parts. If you notice, the CP and the CPK are going to be using the moving range, the center line, sorry, the center line for the moving range that was calculated based on my collection of all 20 of those parts. It does not change based on whether it's part A, part B, or part C. It's considered a constant for that data set. And then my upper and lower control limits, you can calculate those again based on the moving range. And again, that's not going to change. It's going to be treated as one population of data. So next chart, please. Yeah, so now we have my upper and lower control limits on my value to nominal or value to target. And I've got my control limit for my moving range as well. So all the calculations that we looked at earlier, this is where this chart has the most power and most ability, is now I can say, is my data distributed normally? Yes, because that's the nature of this type of chart. Are my upper and lower control, is all my data within my control limits? Yes. So we would say that for these parts, this process is both stable and capable. So that brings us to the conclusion here. And Andrew, I'll turn it back over to you with 2 minutes to spare. I apologize.
Okay, no problem. So a quick summary on the next slide. One more. So these tools are easy to implement and understand. Don't forget about checking for normality. We don't get the advantage of the central limit theorem because we're not taking averages, as Russ indicated. And they work pretty well for small lot sizes that are pretty common in our industry. Next slide. So more webinars coming up. There's one in June for how I choose which control method I need, and then others in September, October, November, and December, which are listed here. So, and they're listed under the events page on the AASQ website. Next slide. And they're free. The best part is they're free, right? So Q&A, we're going to quick look. We have a few questions. The first one, maybe for Becky, actually. Is there a cost to join AASQ? Becky, can you unmute?
Yes, so we have 2 levels of membership. We have the steering group, which is a fixed group of 10 member companies, but we do have the option to join as an AESQ contributing member. and that is a annual fee of $1,000 a year. So if you just go to the AESQ website, click on the membership tab, everything is there for you.
Okay, next question. Maybe Russ, you want to take this one and try? Please speak to machine capability versus process capability and how to isolate toolware from machine capability study.
Oh boy, that's a good one. I don't think I've ever isolated machine wear, although you can see the pattern if you do one of these. If you do control charts, you can usually see that pattern.
Or toolware. I think
or
it's a toolware.
Yeah.
Machine capability, you could check with a laser and other equipment, ball bar type thing to isolate the machine capability. Versus process capability, it's the whole process, everything together, right? So it's good to understand the two and compare them. To isolate toolware, a little more tricky, perhaps, but maybe you can see a trend, like you mentioned seeing a trend on the chart to indicate that there's a consistent shift.
That's usually changing. Right. Yeah, that's usually what we see, and we can usually assign it to that cause. But yeah, measuring process parameters, like how many parts go through that particular tool before I kill it and replace it. That can be coupled with a control chart for TPM, or total preventative maintenance.
One more question. We're a little bit over time, but this will be a quick one, I think. PPK or CPK, which is better to use? Specifically, when you have a PPK that beats the customer requirement, but a CPK that falls a little short. We've debated this as a SMIG team many times, and probably within each company debated it. And we're actually moving towards standardizing on PPK in the next revision. And because it gives you a little more robustness in the results, it's looking at the longer term variation, and typically usually your PPK is worse than your CPK.
Yeah.
Usually. And if the PPK gets as good as the CPK, then you're doing well in the longer term sense, getting rid of those long term variations. So anyway, that's all the questions we have, and just like to thank everyone for coming. There'll be a link coming out, and I think we'll skip the questions, the quiz. We'll save that for next time. And thanks for everybody for participating and joining us.
Yeah, thank you very much.
Have a great day.
Yeah. And then there were two. Looks like Becky had to go too.
That's it. Yeah, Becky's gone too. Good job, Russ. Thanks for stepping in to do this. Good to hear your wisdom on the topic.
And your experience. Thank you too, Andrew. I appreciate. I didn't know you were part of the SMIG, so that's good to know.
Yeah. Trying to make a little contribution. All right. Yeah, we go on.
Bye.